This is a production of Cornell University.
What I'm going to do today is we're going to start with pH, sort of the intro lecture to pH, and then we're going to go back to this at the end of the lecture. Okay? Now, this is the third of a series that I think are really important. You've heard me, we've already talked about the texture mineralogy. We just got done with organic matter. The last of the really important, I mean, not that the rest of the semester isn't important too, but from my perspective, the three most important series of lectures are organic matter, texture pH, and then this one, which is, let me try this again. Organic matter, texture mineralogy, and then this one, which is pH. Okay, so to start talking about pH, we're gonna sort of, what is pH? And then we're going to sort of relate it to what soils are. And then what we're going to be doing from there is then we're going to start talking about the processes that actually produce pH. What are the, and that's what basically today's lecture is all about. Okay, we're going to get you guys up to speed as to what pH is. We're going to relate that, why pH is important to soil. And then we're going to talk about what are the processes that in fact produce protons and hydroxide. What are the things that produce these pHs? Okay, so this could easily just say acidity. It doesn't necessarily have to say soil acidity, okay? But we're going to be talking about soils. So what, in fact, is acidity? Well, it turns out that water disassociates, okay? And it disassociates at a constant, okay? Water basically disassociates into protons and hydroxide. If you can put these two together, it's going to be water. But it disassociates at a constant at 10 to the minus 14th. That means 1 out of every 10 to the 14th water molecules in a glass of water is disassociated. Okay? Now, both of these are present, but they are in fact disassociated. Now, the measure of pH is a measurement of the concentration of the proton. There is also something called pOH. Has anybody heard that one? Okay? Basically, that's the concentration of hydroxide. But interestingly enough, if you know the concentration of this, you know the concentration of that. And I'll talk about that in a moment. Okay, so basically about 1 in 10 million water molecules are disassociated at a given moment. Okay, now these water molecules will reassociate, but another water molecule will disassociate. So it's at this constant of 10 to the 14th. Therefore, the ion product of this disassociation is a constant at that 25 degrees Celsius, and that's that constant. Okay? Now, this number here, if you think about it, and remember we're talking about pH, this number here should mean something. What's the scale of pH? 14. Up to 14, 0 to 14. Okay. Therefore, when water is pure, this disassociation is equal. There's going to be an equal part of protons to hydroxide. Okay, so this disassociation right here of protons to hydroxide are going to be the same. So the concentration of protons is going to be 10 to the negative 7th. The concentration of hydroxide is going to be 10 to the negative 7th. When you multiply the two of them together, you get that constant of 10 to the minus 14th. Right? Does that make sense to everybody? Now, the reality is, though, in the real world, these concentrations of hydroxide to protons can change. They can flip. Okay, so as the proton concentration increases, the pHs go down, the hydroxide concentration decreases. Okay, this is a constant. So as the concentration of this goes down, I have an increasing concentration of protons. As I have a decreasing concentration of protons, I'll result in an increasing concentration of hydroxide. They're always in balance to that constant. Does that make sense? Now, one little caveat. The reality is we can, in fact, blow past this constant. We can make things that are more acidic than 1. We can do it in the lab. In fact, we often do it when we have acid mine waste. But this is where the scale comes from. One way to take a look at this is what's straight out of your book. This is the concentration. Okay, so here's the constant negative 10, but this is how many zeros we're looking at from the decimal point. Okay, this is pH. Okay, as the pH increases, the concentration of protons is going down, which means the concentration of hydroxide is going up. Does that make sense? When you get to the pH of 7, they're at equal concentration, 10 to the minus 7th. Cool beans? Questions? Pretty straightforward? Now, how do we actually get to the pH scale of 1 to 14? Basically, we take that constant, whatever it is, and we apply the negative log to it so that it's an easier number to look at, in essence. Okay, so if the concentration of the protons is 10 to the minus 6, the pH is 6, because what we do is we take this concentration and we apply the negative log to it and we turn it into the pH of 6. Right? So if the pOH is 10 to the minus 8, minus 8 plus minus 6 makes the minus 14. The pOH is 8. Does that make sense to everybody? That's how we get the conversion to the pH scale of 1 to 14 versus saying it's 10 to the minus 1, 10 to the minus 2, 10 to the minus 3, 10 to the minus 4. Does that make sense? Okay. Finally, we're almost there, guys. Finally, as the ion concentration is always maintained at this constant, at a pH of 5, my proton concentration is going to be negative 10, my hydroxide concentration is going to be negative 9, and my total constant is 10 to minus 14th. So at a pH of 5, my pOH is 9. So 5 plus 9 is 14, right? We do the same thing here. At a pH of 8, my proton concentration is 10 to the minus 8. My hydroxide concentration is 10 to the minus 6. Gives me a concentration of 10 to the minus 14th, that constant. pH of 8, pOH of 6. Make sense? Cool beans? So as a result, if you know the pH, you know what the concentration of hydroxide is. Because I know what the concentration of the acid is, the protons, and I know it's at a constant of negative 14. Therefore, I just add it to the 14, or subtract it to get what the pOH is. Cool? Take a deep breath. You guys survived it. All right. Let's give you some idea about what this actually means in the real world. This is straight out of your book. Okay, and what I did was I basically took some of these and added some other ones. But basically, this term is very strongly alkaline neutral. And I gave you some ideas about what things are at that pH. So neutral pHs, basically 6.6 to 7.3. You're looking at things like saliva, blood, shrimp. Hey, come on, it was cool. You had to put it in there. All right, at the extremely acid end, you're looking at less than 4.5. You're looking at things like vinegar, stomach acid, soda. Okay, very strongly acidic, 4.5 to 5. You're looking at beer, tomatoes. Okay, as you move your way down through this system, you get to moderately alkaline, 7.8 to 8.4. You're looking at seawater, sodium bicarbonate. Okay, this is one of the reasons why we take sodium bicarbonate to settle our stomachs. When our stomachs, we have an acid reflux or something like that. We throw this in, it neutralizes the acid that's in our stomach, brings it back down to more neutral. Okay, not that our stomachs are not acidic as they are already. Okay, very strongly we start getting into borax, 8.5 to 9, and very strongly we're talking about milk of magnesia, ammonium, and lime. Okay, just to give you some ballparks, these are things that you guys all know, right? Is anything in there that's unfamiliar? Lemon juice, I mean, eggs, 7.6 to 7.8. Okay, cool? Okay, so that's the pH. Now, let's talk about where this stuff is. Now, the assumption, I mean, generally when people start talking about pH, they generally start thinking about, well, you know, where is that acidity and, you know, what's going on? Well, if you look at the landscape of the planet, red basically means acidic, yellow basically means neutral, blue basically means basic. Okay? And you can see that as you move across the planet, there's a lot of distribution of acidity, or pH, across this space. Now the question then is, well, what's controlling this? Why is this acid and this is alkaline? Now it has huge consequences on things like agriculture and engineering and water quality and things like that. But let's take a step back and say, why is it in fact acidic? What's going on? Okay? And that basically is what we're going to be talking about the rest of this lecture. Okay?
This has been a production of Cornell University, on the web at cornell.edu.